Hello guys, today we're gonna start with chapter 2, and basically it's gonna over the architecture of the hardware meaning, and this you can go over in the architecture class, and usually it's for computer engineers. You won't take it, but I think it's useful in assembly to know the under layer, which is the hardware. I'm gonna try to go over in 1 or 2 classes. Hopefully we'll finish it today. But remember, after this, we're gonna go into the MASM programming. Hopefully you downloaded the MASM and it's working, so we can start the program in the next couple of days. Okay, let's see. Today we're gonna talk about the x86 processor architecture. And what's the x86? x86 is a family of processors, usually Intel and AMD. Those are the most widely spread in the market known for processors. Intel I think takes about 75 to 80% of the market, and then AMD takes about 20 to 25, but AMD is picking up now. It has really nice features in their processors. The x86 processors, we're going to talk exactly about the IA32 processor, which is from that family, and actually it's the 8386 processor, and it was built or introduced in 1985. Before that, processors were 16-bit and 8-bit processors, meaning they only take operands 8-bit and 16-bit. The AI32 came with the 32-bit feature. It can handle 32-bit feature. It was the first processor, and the x86 processors family started in 1978. I think that was the first processor, the 801, 86 processor. And on each generation, they add more stuff on it. I think on 93 came the Pentium, or yeah, so I'm not into those that much, but it introduced also the AI32 memory segmentation, added more memory than covered. For example, if we had a 16-bit memory bus, we can cover 20-bit, which is 1 megabyte of memory, and we'll show you how they did that, hopefully in this. This is IA32 Intel processor. Predecessors were 16-bit, we said that. The one after the successor was the IA486, where they introduced the pipelining, and when we take the instruction for life cycle, I'll tell you what pipelining is. Then came the Intel 64. I think that was the Pentium. I'm not sure. No, I'm not sure about that. The IA32E was similar to the Intel 64, where it took 64 bits as operands. And all of those processors are backward compatibility, meaning I can run I can run it on previous processors or successor processor without the need to compile it again. It will just run immediately. That was a good feature on it. All those processors are done that way. Now let's see, basic microprocessor, microcomputer or microprocessor design. We have 3 main things: the clock, the control unit, and the ALU, and those are the 3 parts of a CPU. A clock to synchronize what? CPU operations. Synchronization between different operations, different units. The control unit is the main unit, and it's the unit that gives permission to every device, asks for the instruction from the memory. It's the coordinator of everything in the CPU. We have the ALU that performs the arithmetic and bitwise operations, processing. ALU unit, arithmetic and logic unit. It performs the arithmetic and bitwise operation. Now this is the microcomputer design mainly. I have here, we have a central processing unit, which has what? the ALU, control unit, and clock. We have here a control bus. We have an address bus. This is the control bus to control if you're reading, writing, and here we have the data bus, where to get the data from. Here we have registers, and we're going to talk about registers soon. Registers are the fastest memory. They're memory. Fast because they're near the CPU, really fast. Here we have the memory storage unit, input and output devices. This you can think of it as RAM. Here the control unit, this is how the central processing unit processes. The control units asks from using the address bus for the instruction from memory. Address bus, data bus grabs the data, brings it to RAM. From where? From disk. Brings it to RAM. From RAM it goes to registers. Then we run it, and we're going to see how this whole process happens in this one. Instruction life cycle. First thing, the control unit fetches instruction fetch. The first thing, fetch the instruction from memory, let's say disk, wherever you have your, and brings it to RAM. Anything that needs to run on the computer needs to go through RAM, needs to be on RAM. Remember the volatile and non-volatile memory we talked about. We're going to talk about it soon also. Then what happens? The control unit decodes, instruction decodes that instruction and knows is it an addition, a subtraction, or whatever the instruction is. Then if it has any operands, if that instruction has, like, let's say an add instruction, let's say I have an add, let's say we're saying num1 and 5, for example. Num1 is a memory location, 5 is a constant. So first we fetch the instruction, this instruction, we fetch the instruction from memory, the add instruction, decodes it, knows it's an add instruction, that the control unit is doing that. The control unit fetch the operands, num1 and 5, fetch them from memory, puts them on the registers, and then execute the instruction, and whatever results from this, I'll do num1 plus 5, add them and save it in num1 and write back to memory. Save the result back to memory, store it. This is thinking of like load and store. Sometimes they're called load instruction from memory and store. Here we can say store. This is the instruction life cycle. Here the memory hierarchy, and you all should know it by now. What's the memory hierarchy? We have on the top registers. They're really fast, so expensive, and there's we don't have that much registers on the computer. If you calculate the size of the whole registers, it's not gonna even be 1 megabyte. And the reason for that is they're so expensive. So expensive. They came out with cache, let's say level 1, cache to increase the performance and make memory faster, where we usually save most frequent used data on the cache better than saving it on where? On RAM or disk. Whenever you use it, it stores it, keeps it on most frequent, most recent used locations are kept, or data are kept in blocks in cache level 1. So if the CPU or needs it, it doesn't need to go back to RAM or disk to get it. And we have also cache level 2, which is bigger than cache level 1. We can also have cache level 3 depending on the computer, the architecture. We have then RAM, which is physical memory, which is where everything needs to run. And here when you start your computer, what happens? You load your operating system, or you load it to RAM so it can run. Because when I turn off the computer, all this is deleted. Anything on those 4 memories is deleted or wiped. We won't have anything on it, volatile and non-volatile. all the data is left on the disk. Disk is permanent. This is temporary memory storages. They go when you take it out of the electricity or turn it off. So we need the operating system on disk. We need to load it on RAM. Anything that runs on the CPU need to go through RAM. Needs to be on RAM. Then cache 1. This is to increase, and registers are on the CPU, which makes them really fast. And here's size. The way size goes, register has 2 small caches. Size grows this way. Disk is we can have 1 tera now, 2 tera, and speed goes also that way. Speed, meaning speed, or let's say time to access. Time to access disk is really high. It takes so much time to access this. It's far from the CPU and it's big, so it needs more time to access a memory location. In price also, it goes this way. Price goes this way. Registers are the most expensive. That's why we don't have that much registers on the computer. Think of having a terabyte of registers. Can we do that? How much is the computer price going to be, and how much speed are you going to gain? Now, the most important, those are really important registers to know on the IA32 architecture. Really important, guys. If you don't know those registers, you're not going to be able to program. We mainly have 8 general purpose registers. They call them 8 general 32-bit registers, each of size 32. 8 32 registers. 8 32 bits registers. We have 4 of them can be used as 8, 16 or 32. Remember, they're backward compatibility. So I have EAX, EBX, ECX, EDX, and this is accumulator, E extended accumulator, extended base register, extended counter register, extended destination register, and those we can break down into what? 16-bit, 8-bit, 8-bit high and 8-bit low, which is, we can call them, when we access them, we can call them AL and AH. When I use those AL, AH, I can't use this part. We can't use that part. I can use the 16-bit if I'm using 32-bit, all of it. And how can I use all of it? I can say EAX. EAX, for example, I can say move. This is a command. EAX, and we can say 5. Just move 5 to this entire register. If I say move AX5, it moves it to this part, the A low and A high, meaning save it. If I say move AL5, I can say that also. It moves it to this part, this one here. If I say A8, move 5, it will save it in this part. So this is how we can use what? This is 1 byte. 8-bit is 1 byte. 1 byte. So I can use it as either 1 byte, I can use it as 2 bytes, and I can use it as 4 bytes, which is 32-bit. Those are the only registers that I can divide or split into small bytes. EAX, EBX, ECX, EDX. So those are really important registers. We have also, we have EDI, destination index, source index. Mainly used, those are used with the arrays and strings. EDI, destination index, and source index. Think of them. We're gonna see how we use them with strings and arrays. This is extended stack pointer and extended base pointer for the stack also. Those are for the stack, extended stack pointer and extended base pointer. And for actually what they say is the first one, and this we're going to show you how when we call functions everything is saved on the stack and how the stack works. This is really important to know on a lower level. You've been programming C++ and you haven't heard, I think, anything about stacks. And this is now it's the time to know what is a stack. And basically it's first in, last out. A stack is first in, last out. First in, last out. L out. F-I-L-O. And BP is the base pointer, points on different location in the stack. It varies. The ESP, the stack pointer, points at the start of the stack, always points at the start of the stack. Then we have another that goes up and down depending on our memory. So those are 8 32-bit registers, general purpose registers. We have two more 32-bit registers, and we have 6 more segment registers, let's say, which are 16-bit. So we have total of 10 32-bit registers and 6 segment registers. Let's see, 2 dedicated 32-bit registers. Dedicated, we have the EIP, extended instruction pointer, or sometimes you might hear of it as program counter, PC. Sometimes some books call them program counter, PC. It holds the address of the next instruction to be executed. It's a register that holds the address of the next instruction to be executed. Remember here what we said on the, let's see, the control unit on the address bus puts the address of the next instruction, goes grabs it from disk to memory and brings it back to here. Think if I had the address already here on a register, this will make the whole process much faster. I'm processing an instruction now. While I'm processing that instruction, I'll get the address of the next instruction and I'll put it in a register to make it fast. So when I start executing the next instruction. We have the E flag. There's flags. We have flags. What's called a flag is if something goes wrong, I'm gonna flag the CPU. Just 1 bit. We have 32-bit. We have 32 flags. Some flags are 0 flag, and this means when the destination is 0, when I get a result in any arithmetic operation, when I get a destination that is 0, I will flag the CPU. So how do I flag it? I will set the 1 bit in the E flag register. Let's say this is the E flag register. Oops. And we have 1 bit here. Each flag is a bit. And we have 32 bits. So let's say this is the 0 flag. When a result is 0, it will change the flag bit to 0. Parity flag, sign flag. When the result is negative, it will put 1. What we mean by a parity flag, a parity is when I have, if you know, here's a message, let's say, here's data, 1 minute, and we have what? Let's say this is 7, this is 7 bits. I add 1 bit as a parity bit to any message or data, and we count the number of ones. 1, 2, 3, 4, 5. If I'm using an odd parity, this is what's called odd parity. If I'm using odd parity, I have 5 ones, so here I'll have 0. The parity bit is 0. If I'm using even parity, I have 5 ones, so I'll put another one to make them 6. So the parity is the number of ones in a data, including the parity bit. This is really important, guys, including the parity bit. So this is 6 and I'm using even parity. That's right, I have 6 ones in this message, including the parity. I'm using odd parity, I have 5 ones, and this is 0. That's right. And usually we do this, like let's say I want to send a message to one of you guys. I'll add a parity bit, I'll send this message. If something went wrong during the communication and this bit was wrong, and let's say now it's 1 and we're using even parity, we count the number of ones. You get a message 1 1 1 1 1 1 6 1 with the parity bit as 1. So now you count them. Now you have 7 bits, and we're using even parity. So you figure out there's something wrong. Something wrong when Gabe sent me a wrong message. So I'll reply back to Gabe, you sent me a wrong message or something. This is all set in the handshaking. This is usually in communication. So don't worry about it that much, but know the meaning of a parity bit. So a parity bit counts if the number of ones is even. I'll put 1 in the parity flag. We have an overflow. If I have an overflow, I'll put 1. If I have a carry flag, I'll put 1. And the CPU, this is really important. This is the only register that the CPU deals with this way. Every clock cycle, the CPU goes and checks the flag registers, checks if there are any changes. Meaning, did the destination be 1? Did it change? Did I get a 0 flag? Checks its flags so and this is depending on the programmers or depending on the architecture, how they program. This is up to them. Like I want, if you get a 0 flag, just output a message to the user. If you get a parity flag, do this. If you get a sign flag, do this. It depends on the programmers, how they wanna, the developers, how they wanna develop their app, what they wanna do with it. So those are the 2 extra with the previous 8 32 bits. Those are all 32-bit registers. EIP, really important to know, holds the address of the next instruction to be executed. E flags, which has 32 flags, and we have 6 segment 16-bit registers: code segment, data segment, stack segment, extra segment, and we have the GS, FS, and I forgot what GF and FS stand for, but those are extra segment registers, and those are smaller registers which hold 16-bit. This will hold the address of the code segment from its name, where the code is. And usually here's how memory is, usually, not always, this is how memory is divided to. We'll have, I think if I remember it right, we'll have here the code part, we'll have here the stack part, let's say, and here we have the extra part, the extra segment register, and here we'll have the data. And what will the DS hold? The address of this part, the 16-bit, that point here, the code segment, and stack, and ES. This is usually how holds the address of each part segment. So now I know I have what? A memory of size 16-bit, meaning 2 to the power 16. And what's that, 2 to the power 16? How much is it? You got 64 kilobyte. 64 kilobyte of memory. But in our architecture, it deals with 2 to the power 20, which is a 1 megabyte. 1 megabyte, 22 to the power 20. So we're gonna see how we got an extra 4 bits for this. So mainly, guys, remember, registers are the most important, and I'm gonna go over them a lot. We have 8 general purpose registers. which are 32-bit each. We have 2 dedicated 32-bit registers, which are the EIP and E flag. Remember those, I have 4 which I can divide to smaller parts, like 1 byte 8-bit or 2 bytes 16-bit. And I have 6 segment registers which are 16-bit. Those are 16 registers that we need to know about. You need to know about it, guys. They are really important. Here they are. EAX accumulator. This is an accumulator register which it's mainly involved in every arithmetic operation. We have an EBX is a memory pointing into the data segment. This is an EBX. Usually we have here memory pointing to a data segment. ECX, here we use it in looping, a counter. We see how to use that when we create loops. EDX is also an extra data used for extra data register. Usually this one is used for multiplication and division, and we're gonna see how that happens. And those we know we took when we use the stacks. We're gonna know when we use strings or arrays. We're gonna know how to use those. So guys, please, 32-bit registers, those that can be divided into 1 byte or 16-bit, and those are those 4 can only be divided. Those and those we can play general purpose registers, meaning even if I don't have a loop, that doesn't mean I can't use the ECX. No, you can use it. But when you're using a loop, when you have a loop, it's really important not to use it. You can use it, but you don't want to change the count of the loops. You don't want to change the count of the loops because it's going to be stored in the ECX. We have also, those are extra registers. I don't think we'll be using them for now. And they're floating point data registers, and they're 80-bit. ST0, ST1, they're called to ST7, arranged in a stack, used for all floating point arithmetic. This is where we have some now processors have what? A floating point unit, was called FPU, and this unit deals with floating point operations and arithmetic. Why? Because floating point operations are expensive, so I don't want to keep the CPU busy with those operations. They added a floating point unit to the CPU where it deals only with floating point arithmetic, and they have their own registers. This made the floating point operations faster and don't cost that much. There's not that much penalty on the CPU for using them. Penalty meaning not much time. It's not wasting that much time. We have 8 64-bit MMX registers. Math, what does MMX stand for? I forgot. Math matrix extension. I think math matrix extension, and it's used for do you know single data, SID, single instruction, multiple data, where I can have, for those registers, I can have more than one input at a time. So let's say this is the input to the registers. I have 8 registers. I can deal with them as one data. So those are 3 registers. I'm using 3 64-bit registers, so it's 128, and another 64 is 192. Is it 192? 128 for 192. So this will deal with a 192-bit data, and it will take it all as one part. Single instruction. If I'm adding what? Add a 192-bit operand. and I'm gonna take all those three as one input. So we divided them into three parts. We took them single instruction, multiple, 1, 2, 3, multiple data, and we can use that using the math matrix extensions, and usually those are used in let's say matrix multiplication, and we take that in linear algebra. I don't want to go into, but speeding up things in matrix multiplications is really important. There's lots of things that are based on matrix multiplication in computers. We have also 128-bit, same as those, but they introduce a 128-bit, so they say the extension matrix multiplication register for single instruction multiple data operations. Those I don't think we're gonna go over them. We're not gonna need them, even though we're using floating points. I'm gonna show you how to deal with that. Always smart programmers tend not to use floating point operations. They usually tend to know how to overcome this problem. Why? Because they're expensive. So we're able to finish this real quick. That's good. It might take 2 lectures, but I went really fast over it. So please guys, know the registers. This is the x86 architecture. X stands for different version, 801, 802, 803, different 8086, 186. There's lots of family. We're gonna be talking about the IA32 architecture, which has the registers I talked about. Know the registers is really important. We have 10 32-bit registers. 8 are general. 4 of them we can divide as we want to 1 byte, 2 bytes, and the other 4 we can use, but I'm gonna show you how we can use them. They're mainly used in stacks and arrays and strings. And we have another 2 dedicated, which are the extended instruction pointer, which is also called PC, sometimes program counter, which holds the address of the next instruction to be executed. And we also have the E flag, which holds flags. And remember, we will flag in it to tell the CPU, whoa, something happened here, hey, stop. Or we flag the CPU, but we put that in a 32-bit. Each flag has 1 bit, and usually it covers what we need to do. And we have the 16-bit segment registers, which is code segment, data segment, and stack segment. Those are the ones we'll be using, hopefully. So guys, please try to install Massive, and see you next class. Next class we're gonna start with Massive format, instruction formats, and talking about the instructions so we can start applying it and programming in Massive. But guys, you have to know the architecture, the hardware. Don't think this is theoretical, not important. Please go over it at least.